So Steve was really good about talking about security locally, and the question came up at the end, well, what happens if you're going over the network? And that's where we need cryptography. So that's what I'm going to be talking about a bit. So some of you might know about security. Some of you, this might be relatively new. You're focused on chip architectures. I'm not very familiar with chip architectures myself, but I can talk about cryptography. But I want you to think about right now, when you're trying to do cryptography on small devices, just to think about what you need. Trying to secure it with a public key technology. And I'll explain what that means in a second. But you've probably heard of some public key technologies. So just think about trying to secure your really, really small devices with public key. And really, think, can it be done? Eric said earlier, earlier today, saying, well, just make sure your chips are big enough to support the cryptography. Well, that doesn't always work. I'm not going to put a huge Intel 64-bit chip in my smart light bulb. So you have to sort of balance. So can it be done? Let's think about it. Well, let's go back a step to symmetric systems. Why not just use symmetric? A symmetric system, something like AES, the Advanced Encryption Standard, you have two entities that are talking to each other, and they share a key. You use symmetric systems every day when you have a secured Wi-Fi, because you have a password that's connected to that's configured on the access point. You enter that password on your computer. It's the same key and same password, and that gives you access. Why not use it? It fits. It's fast. Great. Let's do it. The problem is it's hard to deploy. So let's go back to that Wi-Fi example. If I have 100 people using the same Wi-Fi, I have to get that same password securely to 100 different people. Now imagine if those people are distributed throughout the whole world. How do I get a secure password to someone in New York when I'm sitting here in Mountain View? That's the problem. That's one of the main problems with deployments. So it's just really hard to deploy because of the key management problems. And it doesn't scale. Now take that to 100 people. Now take it to 1 billion devices. So you either have 1 billion devices that all have the same key, at which point you break one device, you break the whole system. That's, again, going back to Wi-Fi. Or you have 1,000 devices that have individual keys, and now you have to have this database that everyone has to have access to securely, because if someone has access to the database, then they can forge entries in the database. So it just becomes a very big deployment nightmare. So this is why we want to go back to public key technologies. The problem is, public key has a bad rap, in particular on very, very small devices. So why do people think that public key doesn't work? And generally, there's a few common conceptions or misconceptions, depending, about it. One of them is too big. The code for public key technologies is just, when it has to do a lot of things, it just doesn't fit because the code's too big. Sometimes if you can get it to fit, it's just too slow. It doesn't meet your performance requirements. Or if you can fit and it meets your performance requirements, it just takes too much energy, in particular if you're a battery-powered device, to actually be effective and just take your battery life to 0. So I'm afraid to say that the bad news is a lot of those beliefs are actually true. Speed. Even ARM, I know this is just 5, but ARM has done a lot of testing on elliptic curve cryptography. Elliptic curve is kind of the current modern go-to for public key technologies. They've spent a lot of time and effort on doing performance testing and analysis. They can get performance on some of their Cortex-M processors down in the 200 to 1,000 milliseconds. That might not sound like a lot, but if you're trying to do a lot of accesses, a lot of operations, it still can add up. And if you're trying to boot up a system, okay, I'm gonna have to wait this time. Imagine that in a missile guidance system or something like that. Size. Again, doing research, you're getting sizes in the 8 to 30 kilobytes of ROM and 800 to 1,000 bytes of RAM to get these systems working. Again, if you're dealing with an Intel processor or something that has lots and lots and lots and lots of memory, great, you've got the resources. But if you want to do these small embedded solutions, you don't have that luxury of having all the space, because that space you can use for something else, like your actual application that you're trying to program. And hardware implementations. Well, if you're going to go down to hardware and talk about putting an FPGA or into an ASIC, yes, they're faster. but your ACC implementations are going to take a lot of gates. And the reason about this is, and the problem, of course, is that RSA and Diffie-Hellman, other public key technologies, which you may have heard of, they can take even longer. So why is this the case? Why does it take so much time? Well, the problem is that all of these solutions, they're basically working on really, really large numbers. In particular, you're multiplying 256 to 4096 bit numbers. And that takes a lot of effort, because you have to take these huge numbers, break them down to really, really small pieces, operate on each piece individually, and then build the answer up. So the bigger the number and the smaller your processor, the more work you have to do. But there's some good news here, too. There's some additional technologies that are out there that have been studied for a while that I'm going to be presenting for the rest of my another 10 minutes. And what I want to talk about is group theoretic cryptography, or what we call GTC. There's a book there I have up on the screen. You can go to Amazon and you can go order that. The book's been out for a few years. It's been studied actually for over 100 years, the math that's behind group theoretic cryptography. The group theory specifically has been studied for 100 years. Applying it to cryptography is a little bit more recent. First started in the 70s, so it's been around for about 40 years or so. But one of the interesting things about this type of technology is that it actually scales linearly. So as you want to increase the security of your system, you'd instead of going up, 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 like you do with RSA or ECC, it just goes up linearly. So you double the amount of security, double the amount of effort, which is actually an interesting property that I'll get to in a bit. So a little more on GTC. It's very small. So it's designed for very small systems. We actually have some implementations on 8-bit processors. We have got an 8051 implementation. It's fast, it's secure, and the other interesting thing is it's quantum resistant. And so what does that mean? Well, quantum computers, people, even the NSA, have been thinking about, well, they're coming out sometime soon. We don't know when. MIT built a 5-qubit quantum computer recently. Actually was able to factor some numbers. So they broke a very, very small RSA key, like a 5-bit key. But if you're going to have devices that are going to be out in the public for decades, 10, 15, 20 years, you're going to have to start worrying about quantum computers, because in 10, 20 years, quantum computers are going to be out there, and a sufficiently large one is going to break any of the existing technologies that are currently being deployed. Another interesting thing about group theoretic cryptography, it doesn't require extended math. So ECC, RSA, Diffie-Hellman, they're working on those very, very large numbers, those 256-bit to 4096-bit numbers. We're dealing with numbers that are like 6 to 8 bits. And that winds up being good for performance. It means you don't need the extra math sections on your processor. So you get a lot of extra performance and you get smaller systems out of it. The implementations themselves are small. The code that it takes to do this math and the stuff around is very small and concise. We get efficiency and speed, and now you can do more important things like actually get your stuff coded back. And basically some of the stuff I'm going to talk about specifically is we have a key agreement and digital signature method for RISC-V. We have other platforms as well. So specifically, we got 2 things I'm going to talk about a little bit. I, again, don't have a lot of time, so I'm not going to do a lot of detail. The first is what we call the Ironwood key agreement protocol. Key agreement protocol is something where you have 2 endpoints that communicate over an open channel. They submit data back and forth. And at the end result of this computation, you have a shared secret. So it basically allows me to give you some data and do some computation, and we both come up with number 17. But of course, no one who's around and listening can compute the number 17, but we now have that number that we can now use to authenticate and encrypt data going forward. The secondary method that we've got is a digital signature algorithm. This allows one device to generate a document and have it be verified by another person. So you can think about this like a certificate, a driver's license. A driver's license is like a certificate. It's given to you by an entity that you trust, and there's a lot of verification, physical verifications on it you can do. And this is kind of the digital equivalent of that. And one of the interesting things about Walnut is very, very fast verification. So how does this relate to RISC-V? Well, we basically took a test platform and implemented these on RISC-V. So we wanted to actually use the Z-scale, but that's not available any longer. So we actually did this instead. We took the Coreplex, the Sci-Fi V3, and we used the, oh, you can read what's up there. I'm not going to read off to you. But the interesting thing is we implemented our code on there, and we started running a bunch of tests. So the first thing we did was took our code, Walnut DSA, and built it, and we compared it to micro-ECC, which is an open source implementation of elliptic curve. And the first thing I should point out is the runtime and cycle counts that you see. So that's how it works. But basically, a runtime for a verification of our signature on Walnut was 4.9 milliseconds versus over 2,000 milliseconds, over 2 seconds for an ECC verification. Now, I do want to point out that is without the multiply divide instruction enabled. When you do enable it, you get a little bit better performance. It brings it down to 450 milliseconds. That's still a significant performance differentiation. And also, you can look at the amount of ROM and RAM used. I know that there are other implementations of ECC that are going to be smaller than this and faster than this, but they're not necessarily open source at this point. Micro ECC is something that is available to everybody. But next, we did another thing. We spent the time and effort to actually code our implementation in RISC-V assembly. And we did this because you can get a lot more performance out of it. In this case, we got about 20% performance improvement. So because by writing an assembly language, we are showing that we care about RISC-V, but also you can get the code smaller, faster, and dedicated in. And finally, we did do a comparison against ARM again, just to show. One thing I do want to mention is that it actually is faster on the ARM processor. And maybe some people in the audience can help us understand why that's the case. Internally, we kind of think it has to do with the way the compilers worked. And the compilers for ARM probably got better optimized code than the compiler for RISC-V. But they're still relatively comparable to each other, within a few percents. So I've got about 2 minutes left for questions. So what we have this available. We can make the code available as an SDK if people want to play with it. We can make the assembly language and the C implementations are available in SDK. So if you have any questions, feel free.
Thanks, Derek. Go ahead, you're up.
Thank you. Sean Halla, Intensivate. Just one quick question. You didn't spend much time talking about how difficult it is to crack this compared to cracking RSA or the other one.
That's true. In the comparisons I did, we did with the equivalent security level. So all this was at 128-bit security level. So a 2 to 128 challenge.
Okay, could you? This is the first time I'm seeing it. It sounds too good to be true. So can you fill us in on why it hasn't been more popular?
Well, we've been out for about 10 years. The original papers were published 10 years ago. And as for why you don't know about it, that's why I'm here to tell you about it. But we can talk about more offline.
I think this group would be interested to know if you had any optimizations specific for the RISC-V to get the performance that good.
Actually, this is purely in software. So this is purely in C and the assembler that we had for these numbers. I actually did speak at the last RISC-V conference workshop, and we did have some hardware optimization. Because we have small operands, 6-bit actual math that was going on, we actually had a hardware implementation where we did 4 of them in parallel, and we got a 3x speed improvement with a 25% reduction in code size and a 2% increase in hardware utilization. But that is not in these numbers here. So that would be on top of these numbers.
Okay. And some people in the cryptography community harp on the need to resist side channel attacks by keeping the cycle count constant and no secret branches or memory accesses. Does your code base do that?
I believe it does. I have to go verify. But the underlying one-way function that we use is by definition a time constant one-way function. So the amount of time you spent is directly proportional to the amount of data you send in.
Okay. This is somewhat related to the previous question. In terms of optimizing the code for the RISC-V assembly, what has your experience been with optimizing code for RISC-V assembly? What types of optimizations does the compiler primarily miss? Is this primarily cleaning up obviously stupid code, or are there more subtle changes you're making to get those 40% speed ups? I would have expected that RISC-V would be relatively friendly to compilers at its current stage because of the extremely simple cost model that Rocket implements. They're relatively simple scheduling compared to other systems on the market.
Let me get your information. I'll get you in touch with the engineer and be able to answer that question for you more succinctly than I can.
And as someone who is working on the compilers, I would be also interested to talk about that from the standpoint of what is the RISC-V compiler doing substantially worse than the ARM compilers?
Okay, we're happy to work with you on that.
Okay, last question.
Yeah, could you elaborate on the time? How did you measure?
You identify yourself, please.
Faisal
Name.
from Berkeley Lab. Yeah.
Sorry.
How did you measure the time? Like, could you elaborate what was the method that you used to compute the time?
We actually
is it the user, the CPU time?
Well, we measured. Well, we just measured the number of cycles and computed time based on that. So that's why I have cycle counts available.
All right. Thanks, Derek.
Thank you.